Okay, team, in this lesson we are looking to push our understanding of derivative, second derivatives, critical points, inflection points, and all that to just like a little bit higher level. So we're going to tackle, these are all AP questions. Some of them are a little more interesting than just like the road delta math ones. So let's take a look at this first one, jumping in. So my function f is differentiable and increasing for all real numbers x, and the graph of f has exactly 1 point of inflection of the following, which could be the graph of f prime, the derivative of f. Okay, so as you read these, it's like important to take notes. So first of all these graphs are f prime, not f. There are questions where they make you pick f, so it's important to read the question carefully, like what it's asking. And then f is increasing, right, for all real numbers x. So that means f prime is greater than 0, and then 1 point of inflection. Okay, so 1 point of inflection, that means that the second derivative is equal to 0 at 1 point, right? And that means that my first derivative has 1 extremum. Okay, so we're looking for a graph that satisfies these two things. So everywhere positive, I'm going to go ahead and eliminate anything that is not everywhere positive. So now we just have 2 to pick from. And now it's pretty easy. So it has just 1 extremum. So we're looking for just 1 point of inflection. So we pick A here. Okay, because this one has 1, 2 points of inflection. Okay, so there's our first one. Next one is like pretty much like the delta math. We just make it a little bit harder. We want the largest open interval in which the graph of f is both concave up and increasing. So let's make ourselves some notes here. So f double prime bigger than 0 and f prime bigger than 0 is what we want. Alright, so we will take a derivative here. So we'll get 12x minus 6x squared is my first derivative. I don't like how that looks. I'm going to rewrite it. So negative 6x squared plus 12x, rewrite in standard form, right? And I'm going to set it equal to 0. I'm going to factor out my 6x, negative 6x, right? And then I have x minus 2. And then my zeros are going to be x equals 0 for my first term, and x equals positive 2. Draw a sign chart. Over here, I'm going to pick negative 1 to plug in. What do I get? I get a positive times a negative is a negative. My middle region, I'll pick x equals 1 to plug in, and I get negative, negative. So that's still negative, right? Nope, just kidding. Negative times a negative, definitely a positive. Then over here, I'm going to plug in x equals 3. So I get a negative times a positive is a negative. So there's my sign chart. And let's see, I know we want f prime to be positive. So I'm looking at this region of my sign chart. Then I'm going to take my second derivative. So I'll do that over here. F double prime of x is going to be the derivative of my derivative. So 12. And then minus 12x. Okay. So this is linear. I'm going to set it equal to 0. And we can see here, like, if I plug in 1, I'm going to get 0. So x equals 1 is my only solution there. And my sign chart. So if I plug in 0 to this, I get a positive result. So we're positive on the left-hand side. And then if I plug in 2 to this, I get a negative result. So we're negative on the right side. Okay. So we want the largest interval for which these are both true, right? So concave up and decreasing. Well, it's true that the function is concave up for everything smaller than 1, but it's only increasing for between 0 and 2, okay? So 0, 1 is that overlap, right? So 0 would be here, right? 2 would be here. We could actually do this. We can switch colors. So here is my concave up interval, and then here is my increasing interval, and we can see that they overlap from 0 to 1. Okay, moving right along. This one, here's where we get away from the delta math a little bit, and this one is a really cool problem. I like this one a lot. We want a graph of f that is concave down. Okay? So we're going to take a derivative, and notice we have product rule here to start. So my derivative is going to be 2 times e to the x. So that's the derivative of 2x times e to the x staying the same, plus 2x staying the same now, and then the derivative of e to the x, which is still e to the x. Okay, then I need my second derivative. Okay, and then the derivative of 2e to the x, still 2e to the x, right? Because the derivative of e to the x is itself. And then notice this is what I started with, right? So I'm just going to rewrite my whole thing as my derivative of that. So I'm using product rule again, but the result is the same. So 2e to the x plus 2x e to the x. So there's my second derivative. And then I'm like, this is hard to see like what's going on here. What we want to do is we want to make a sign chart, but I want to do some factoring here to make this a little simpler. So I'm going to factor out, I'm going to note that each term has 2e to the x in it. I'm going to pull that out. And I get 1 plus 1 plus just 2x here. Okay. So here I'm asking you to think a little bit. So I'll combine like terms. And we want to find critical points. Or really, we want this to be negative. Okay, so we'll talk about critical points though. So notice 2e to the x. If you remember what that graph looks like, it's like this, right? So it's always positive. The smallest like value this could take would be 1, right? When e to the x is when the x is equal to 0, or sorry, it would be 2, I guess, because 2 times 1 is 2, right? So this is my 2e to the x graph. It's positive forever. So I can just kind of ignore that actually. And notice like -1 is going to make this second term equal to 0. So really I have just 2 results here. Okay. To the left of -1, let's say I plug in like -2 here. I get a negative result for this term. And then negative times a positive is negative, right? To the right, if I plug in, say, like 5 here, 2 times 5 is 10 plus 2 is 12. That's positive 12, right? To the right, my result is positive. So e to the x doesn't actually matter that much when we're talking about concavity here, as long as we're multiplying it by something else, because it's always positive. So we want the graph to be concave down. That's where x is less than -1. So let's find that. X is less than -1 is what we want. Okay. So same result, and actually same method as the polynomial ones we did on delta math. We're still using that sign chart. We just have to think a little bit harder about what this function looks like. Okay. Next one's cool. I like this one too. So function f has a local minimum at x equals 1, and the graph of f has a point of inflection at x equals -2. And we want to, I forgot to include this, but we want to find a and b. Okay. Cool. So local minimum at x equals -1. That means at x equals -1, f prime of x equals 0, or I could say just f prime of 1 equals 0. And then a point of inflection at x equals -2 means f prime of x is equal to 0, or f prime of negative 2 is equal to 0. Okay, so those are our conditions here. So let's take a derivative. And some of you guys have run into this before if you've done some of the Aspire to Do lessons. What we're doing here is we're treating a and b and k as if they're numbers, right? So a and b and k are not variables. X is the only variable. We're going to pretend that they're numbers. So I'll show you what that looks like. So f of x, well, f prime of x would be, so first term is just a normal power rule, 12x squared. Then we have 2a to the x. So what I did here, or 2ax, is I did 2 times a power rule and then subtracted 1. And I'm just leaving a alone, as if it were like a 5 or something. Like I would just do 2 times 5 and I'd simplify it to get 10. But because I don't know what a is, I can't simplify this. I'm just going to leave it as is. Okay. B to the, or bx, the derivative of that is just b. And then k, the derivative of k is 0, right? K is just a number. Okay. Now, we know this to start. F prime of 1 equals 0. So 0 equals, let's see, 12 plus 2a plus b. Okay. Seems like that's all we can do here, right? Plugged it in. Let's move on. So we'll keep that for now, and then we will take the second derivative. So f double prime of x, and we get 24x. The derivative of 2ax is just 2a. And then the derivative of b is 0, just like the k before, right? Okay. Now we're going to use this fact. So we're going to say 0 equals 24, plugging in negative 2, plus 2a. So that gives me negative 48 plus 2a equals 0. And then I get 2a equals 48. And look at that. A is going to be 24 here. So there's a. Plug that back in to get b. So 12 plus 2 times 24 is 48 plus b. And then that gives me 60 plus b equals 0. And then b is going to be negative 60. Okay. So same logic as before. The reason I put this one on here is so we can see that like sometimes we can treat variables as constants. A, b, and k are constants. So this is how we deal with those when taking a derivative. Same as if they were numbers. I believe we have just one more. This is a good one too. So on which interval is dy dx greater than 0 and the second derivative less than 0? Okay. So I haven't seen this notation much in this unit, but you know by now that they're interchangeable. Okay. So that means dy dx bigger than 0, that means f is increasing. So let's go straight to our graph before we worry about the second derivative. F is increasing means we can get rid of this part, right? And then increasing, and then this would be and concave down. Okay, so f is concave down. We'll notice here f is concave up, right, from A to B. So we want just B to C. So that is, what is that? 2 only. Just B to C. Okay. So there are your solutions for those 5. Again, these are all AP level problems. Some you might have gotten stuck on, that's okay. Make sure you understand how to do them all before you move on to the quiz.